Welcome to our webinar for Business Intelligence Best Practices for Optimizing Data in Google BigQuery and using multiple data sources. I know it's a mouthful, but we've got a lot to cover. Should be pretty interesting. And we have features like the ability to drill into your data through things like pivot tables, and that really helps you see how your metrics roll up to higher levels in your data. And features like single sign-on, where your users don't need another account and password to remember, and this really helps you also simplify your data management and allows for things like embeddability, so you can use it within your existing cloud-based applications. So a lot of the things that customers ask us when they first start talking to us about BI and analytics is, they may have a lot of data in a variety of different sources, and what they really want to know is what's the best way to structure their data as they're getting started, so that it's better for analytics and BI and easy for reporting as well. And performance is a big aspect of that. And one of the four things that we're really going to cover today are some of the basics in terms of using denormalized data and how we can optimize that with a variety of different techniques. For example, using joins or lookup tables, using nested or repeated records within BigQuery, and then finally, how you can also integrate other data sources using iCharts and Mashups. So, some of this may be a little bit basic for a few folks out there, but, with regards to denormalized data, that's one of the basic essentials for reporting in BigQuery. It's tailored to using denormalized data. Denormalized data is basically your full entire set of information within a single row. So you'll have lots of columns, but that's great for a columnar style database like BigQuery, and it'll cover every single dimension, attribute, and measure that you may want to report on. So you don't have to make that decision on, I need to create a cube or anything like that. You basically just fill in the entire row with all the data that you might want, and you'll be able to go back and say, I want this dimension, I want this dimension, I need this measure, I need to make this kind of calculation. And finally, it may also have some pre-computed fields in it, or data from several sources just baked in. And sometimes that's great. You may actually need to do that. Other times, though, we're going to see how further on in the presentation we can make that a little bit more efficient. And just one thing with regards to specifically with BigQuery and columnar databases and denormalized data is one of the massive benefits that you get is that when you're doing a query, it's not going to scan the entire table. It only scans the columns that you're entering in with your query. So whether or not you're doing direct SQL through the BigQuery interface or using iCharts, you'll only be using the columns that you actually specify. So that's great for performance, that's great for data usage, processing, and it'll make things a lot easier. So we've got a mock CPG data set, consumer product group data set. It's kind of a denormalized example. And it's a mock data set that pretends that we're some kind of clothing manufacturer, and we want to look at information about sales across different brands, brand owners, products, different regions over time, and so to see the daily transactions that occur. This particular data set has about 31 columns in it, about 800,000 rows, and it's only really 235 megabytes in size, but I think it'll be a good indicator of, how the techniques that we're going to show can scale to the size of data that you actually have. A lot of our customers that are using our product with BigQuery, they're working with terabytes and terabytes of data, and these same principles apply. A little bit about the information that's here. I think I brought up the fact that we're looking at date information, as well as the categories of brands, brand owner, product, and then further down the line we've got some metadata about each product there, as well as some measure information. So let's hit a demo of how this may look when you're using directly BigQuery, as well as when you're using it in iCharts. Let me make my window a little smaller so people can see it. So yeah, this is our table that we're going to be working with as a base. This is the schema. This is the BigQuery interface, by the way, if you're not familiar with it already. You see a little preview of the data. And now I'm gonna run just some simple queries. Kind of show you, as I mentioned, the size of the data is about 235 megabytes in size. And I'm going to run a query here. And this particular query is just showing for every year and month the total value of sales from our demo data set. Hit run query. I've got a couple options here also set: no cached results, standard SQL. iCharts uses standard SQL. That's something that you should be aware of: standard SQL versus legacy SQL. And here we get the results, and we also see that how long it took and how much data that it processed: 12.1 megabytes. And that's one of the major metrics that we're going to be talking about here during the presentation, about the different techniques. Other things that you'll probably want to take a look at as you're developing your own strategies for your data structure are, as you put the data in and you start to run queries against it, looking at the different stages, how it looks for reads and computes, also some job information. This will tell you, hey, how many bytes you processed, same information here. As well as bytes billed, can give you an idea of the billing tier. For the most part though, for this demonstration, we're going to be looking at the bytes processed. But we'll also see how different techniques can also affect the bytes build. So in my results, I see for every month, I see every month total values, but I want to actually see it by the individual brand products that are available. And so we have another query, basic stuff. We're going to select our brand product and then the year month information, and then we'll be able to see for every single brand product for every month what our monthly value is. And for this particular query, it processed about 28.6 megabytes. Which is still not a lot, but if you're working with a database that's 100 times the size or 1,000 times the size as the one that we're working with here, this kind of query can scale up pretty quickly as well. So the next thing that we're going to do is we're going to actually take this data set that we're using, this product daily sales table, and we're going to bring it into iCharts. This is the iCharts interface. You can connect to a variety of different sources of data, from BigQuery to JDBC data sources to NetSuite, which is also being displayed here. For BigQuery, you can use your OAuth credentials, or you can also use a JSON service account credential. I'm going to use my OAuth credential for a specific reason, being that we also want to show what the performance is of the product on BigQuery, which you're able to do when you have an OAuth credential like that. You will be able to go back into our query history after we've created a chart and see exactly how much data it processed. So I'm going to load up the table. Loads up pretty fast. And all I'm going to do here is select my year month, gets all my year months, select my product. And what it's doing, it's actually building that hierarchy for a pivot table dynamically by going out and making those queries into BigQuery. And then I'm going to just drop value into measure. So we're seeing pretty much the same type of information that is being displayed within that query that I showed you. Results. Brand, product, year, month, and a value. So bucks for 2015 is 1345479, and it's the same here, but we've automatically formatted it. But what you also get using iCharts as a pivot table is you get these higher level roll-ups automatically. So it automatically goes in and is summing up the sum of all of these items. And it's doing this on BigQuery directly. It's not doing this within our own proprietary system. And that's important because you may have non-additive values in your database as well. And so if you try to do a sum of averages, that's not going to work. Or you try to do a count distinct of a number of count distincts, you're not going to get the right number. So it's important to do that on the database, and that's exactly what we do. So we've created this pivot table. We can collapse everything. We see it's got a variety of months we can drill into each month and look at, and I can build it out, and I can add columns, further rows, so on and so forth. But for the purposes of this demonstration, what we're going to actually see now is we're going to go back into our query history. And how we work is, as you're creating the pivot table, we're dynamically creating the SQL that will query against your data set. And because I'm logged in via OAuth, I can go into my query history and look at this somewhat complicated query that is getting the row level information, doing those aggregations, as well as the higher level aggregations. And what I'll also see is, well, I cached the results, so. What I should be seeing is that the query actually is the same amount in terms of bytes processed. But there is some caching that gets enabled with BigQuery for every 24-hour period, and I've been rehearsing this quite a lot. So it actually says 0 bytes processed. The other great thing about that is because it is being cached, it's no additional cost in my processing. Data results may come back faster because I'm doing the same thing. You might say that I'm being redundant, but BigQuery is at least smart enough, and we've enabled caching as well through every single query to say, hey, don't try to run the same query that I've already ran. Things that will affect this is if the data were actually to get updated, then that cache can be renewed. The other thing that is important to mention is even though we're doing this higher level of aggregation, we're doing it in a smart enough way so that it actually comes for free. So you're not charged extra, or you're not processing extra bytes. It all happens within a single query, and it's processing the same column as the original column in the lower levels. So you don't get any kind of extra level of processing for that. All right, so the next piece that we want to look at is how can we take advantage of some joins and some lookup tables. Now, it's pretty well known, BigQuery columnar database, but they also compress and encrypt all the data that's in every single column, and they do that separately. That is a big savings for you in terms of the size of the data, and will also help increase the speed of the processing and the amount of bytes that get processed. But we can actually get a little bit more out of it beyond just the compression that they have with joins and lookup tables. Especially when you may have some fields that have a low cardinality compared to overall data set, and I'll show you an example of that. And if you're getting data from a traditional data source and doing an ETL process that denormalizes everything, often enough in traditional databases, you'll start to see key value pairs, IDs and values, because that's the way an application has been set up in a relational way. But we can actually use that information to create lookup tables that can be referenced from the main denormalized data set. And finally, you may also have some metadata that exists that you may want to reference from each individual row. So for example, like if you're manufacturing clothing, you may have meta information about the sizes, the material, the color, the cut that it has, all this wonderful stuff, the manufacturer location, and that's on a product by product basis, SKU information. And so in a denormalized way, you can, of course, include all of that information within every single row, or you can use a variety of other methods to get the data from other sources within BigQuery. So what we'll actually find is that using a query to create a join and lookup table, it can actually be more efficient than just querying on the standard denormalized data set. So in the example that we have, we're seeing we have a couple of fields here. One of them is brand product and the product ID. This is really where you're going to have to understand your own data because it will be different for everybody, right? But in this particular data set, there seems to be some indication that these two might be related. Of course there is, because I created. But what we'll find is that there's only 51 unique values in the brand product column. So it's a little bit redundant for us to actually store this information within the denormalized data set across 200,000 rows, 300,000 rows. We created a lookup table, and it just takes up 1.56K. And in this particular case, I've still included it within the denormalized data set. You may want to as well. That's going to be up to you. If I remove that column, I'd be saving the space on that column. So let's go for a little demo here.
Well, the computation is going to be on the lookup.
Yeah, and all the computations are going to be on the lookup table as well. Yeah, and that's specific to the demo that we have here as well. So I've got a new query that's going to basically give me the same exact information, but instead of just pulling it directly from this one table of daily sales, I'm going to reference the brand product lookup table that I've created. And the brand product lookup table, really simple, just the ID and the value. Here are the different values in it. 51 rows, 1.56K. And here's my query. Fairly simple stuff, but the biggest change that I've made is I'm referencing the lookup table using a left join. And after I've done that, I'm referencing not the core table's brand product field, but the lookup table's product field. And then I'm able to group by, order by, all that wonderful stuff. Hit run. And I get pretty much the same exact values. Should be exactly the same. But instead of the 28.6 megabytes processed, I'm only processing 17.8 megabytes. So that's a 38% reduction. And what we'll also see here on the explanation, but in the job field, bytes build 20 megabytes, as opposed to, I think it was 29 megabytes before. Well, this is another metric that you're going to want to take a look at. So I can expand on this particular query and create a whole other query that basically brings in all the other fields. I'm not going to run it within BigQuery, but I'm actually going to create a new data set in iCharts using BigQuery, auth credential, my project, my data set. And instead of just referencing a table, I'm actually going to create a data set off of a query. There are a variety of different ways within iCharts that you can actually do this. But since we're dealing so heavily with SQL right now, I thought it'd be important to actually show that. So I'm going to pop this query in here. Let's do a little explanation of the query here. Again, we're looking at all the fields in the data set, but for the brand product and the brand product ID, I'm referencing the lookup table, which I've also joined here. And you can also see that this particular query, it's not grouped on anything. So I'll be able to group it on anything that I want to, even though every time I reference these particular fields, it'll use the lookup table as well as opposed to the original data set. So I'll go in here. Create the data set. We go out, we look at the query itself, we run some tests on it to see what each individual data type is, and then I have access to all the fields again. Here's my brand product. I can take year, month. I can take brand product. Dynamically building that hierarchy, take the value. And I've done the sum here, but I could actually, do other calculations, or aggregations rather. I could take average, min, max. Those are your basic ones. I could also add a formula that does some other things like multiplies it by a factor of whatever, multiplies two fields together, takes the count, and takes the value and divides it by the count of another field. Lots of wonderful, crazy things that you could do. But I've created this pivot table. I'm going to reload and see if it actually still is using the cache results. And if it is, I'm going to change the query a little bit. Okay, the most recent one is the one that we're looking at. Nice long query. And you can actually see that we're basically doing some multiple queries here, but it's using a cached value here, so it didn't have to process any data. What I'll do is I'll just switch brand product and year, month out. It'll change the hierarchy of the pivot table, so that I'll be able to see, hey, Bucks Campers, all the different brands, and then be able to drill into the brand. And I'm also seeing now different numbers for the higher levels of aggregation. So let's refresh BigQuery. The query history again. All right. Nice long query. And again, only processing 17.8 megs of data. It's the same amount as the hand-tailored query that I originally entered. So this is a good indication about how BigQuery actually performs. Even though I created this query that includes all these other columns, my core query that wraps around it to select only the columns that I really wanted is being optimized so that when the query actually runs, it throws out all this information that I'm not using. And so it doesn't process it, it doesn't get billed, so I'm still in the same level of doing a hand-tailored query. And so that's really going to be important for you to when you're exploring your data, that you could definitely go in, explore the data using SQL and BigQuery and tailor a whole bunch of things, and that's great. Not all of your users are going to want to do that. So using a product like iCharts is really going to help them explore that data at the same level that you are without kind of additional overhead. All right. Now we're going to get into some more fun. I think nested data is possibly one of the most awesome features within BigQuery, and really shows the best potential for providing performance increases and optimization. And again, you're going to have the best understanding of your own data, and that's where you're going to be able to see that often enough the data itself will have an inherent hierarchy to it. And when that happens, you're going to be repeating data for every single row in a standard denormalized table. And this hierarchy, some examples are like city and state. The ones that we have here are brand, the product to the brand owner. Dates have their own inherent hierarchy, year to month to day, hour to minutes. So these levels of hierarchy that are there can provide the opportunity for you to actually nest the data within BigQuery. And that'll eliminate redundancies on a per row basis. And so those higher levels, they'll only take one row, and the leaf nodes or the leaf levels will take up the rest of the space. And so especially in a denormalized data set where you'll have lots and lots of columns, if you're able to establish the information that is redundant, not necessarily redundant, but the same on a variety of different fields because of a natural hierarchy, that's an opportunity for you to nest the information. And with BigQuery, when you're nesting data into the individual nested records, so to speak, and repeated records, all those columns, all those fields, they're stored as their own separate columns. And so again, just like this, your regular denormalized table, you're not getting penalized for any kind of column query for things that you don't actually query. Even if you query on a single nested column, maybe you have 5 columns that are nested. If you query on one of them, you don't get processing for the rest of the columns within that nested hierarchy. It'll only process the ones that you're querying. So overall, when you're doing the reporting, using nested data will process a heck of a lot less data than a traditional denormalized table.
Looks scary, but it's much less.
Yeah. This is our demo structure here, and again we see a whole bunch of columns here, and then we have below that we have our nested data. It's called a nested record. It's listed as repeated, and we have information here such as date, year, month, day, and we're nesting also the region and department and the value. So that's basically what we've done. We've created in SQL terms an array of structs, and so each row within this nested record has these 5 fields within it. And if we were to preview the table, and we can do this also, this is basically what it would look like. We're taking the brand product information, and as well as for every single month. And then we're nesting daily transactions for each one of those brand products across the different regions and the different departments. And so what we actually see when we've done this, and it's going to be different for every type of data set that you have. So you'll see more or less types of optimization within your nested structures. But with this particular structure that we've created, this data set is only 34.8 megabytes in size. This is versus the 235 or so megabytes originally. So that's an 85% efficiency increase there in terms of size. So that will affect your the size of the data that you're just storing within BigQuery, but it also affects the amount of data that you'll be processing if you make queries against the nested columns versus the non-nested columns. If you're using the non-nested columns, you're going to be using a tiny fraction of the data that you'll have in your data set overall. And if you're, again, using some of the nested columns like we'll be doing, you'll still be using a fraction of the data that you have in the data set overall, because you're not using this, you're not using redundant data over and over and over again, especially if you're grouping on a column that's not nested and doing an aggregation on a column that is nested. And that's exactly the example that we're going to put in. Yeah, you're skipping all of it. Drag my window back here. Can't drag it all the way. Okay. We have another simple query that references the nested data. And so, actually first let me show you the nested table itself. The same thing that we saw in the presentation. Here's my nested records. Here's a preview of the information. This is all the nested level information. And again, back out to the non-nested information. All this information is metadata, which I could actually include in a lookup table, but haven't. So I'm going to basically run this query. And I get the same exact results and same number of rows, same values, but instead of processing 28.6 megabytes like a standard denormalized data set, I'm only processing 5.73 megabytes. That's tiny. It's 80% reduction. And the bytes builds are 10 megabytes. So those are two metrics that you'll really want to check out when you're using nested structures. So that's cool and all. We'll go ahead and create that larger query again. And that will pull in all those columns again, but unnest. And this is that unnested value here. Unnest those records. That's one of the typical ways that you're able to access the nested level data, by using a cross join to the unnested values. And then instead of saying just the date, year, month, region, I include this information, this dot notation here for that record. Let's bring that into iCharts. Again, I'm going to use a query. I'm not grouping on anything. So I'm still going to be getting that row level information. Now it looks very much like the original data set that I had. I've got the brand product, and then I've got the value information here and the rest of that data. And I can pull anything in here. Brand product.
It's flat from the user standpoint.
Yeah, it's flat from the user standpoint. Good to know. So again, same exact information, flat from the user's perspective. What we'll probably see here is when I do the refresh to look at my query history, it'll probably be using that cached level data again, but that's cool. I'll just change the pivot table to switch it around. This is our nested query. It's doing the cross join. Yeah, 0 bytes because the results are cached. Switch this around. I could have also just changed the aggregation. It would do the same exact thing. Perhaps I'll do that with the next example. And 5.73 megabytes processed, 10 megabytes billed. Now, if we really want to go crazy, we can combine nested structures and lookup tables together. And I think this is probably really going to be an interesting example because this is really where you're going to want to do some of your own tests to see if you're actually going to get some performance optimization out of using those two techniques together. So in this particular example, we're using the lookup table for the brand product, that information. So we're using a smaller amount of data, just that ID within the core data set, and then referencing the lookup table for the brand product name. And then we're doing the cross join with the nested record to get the value and do the aggregation there. So same exact results, right? And ooh, look, 5.71 megabytes processed. We've shaved off about 20K of processing. But let's look at the job information because this is probably the most interesting piece. Instead of the 10 megabytes build, we actually have 20 megabytes build, and that's because we're referencing that lookup table as well as the information that's stored in the nested record. So this will really depend on how you're structuring your information, how much gains you're actually going to be getting from a lookup table versus your standard denormalized or nested data set. Now, if I had a lookup table that only had a couple thousand rows in it, but my core data set was terabytes in size, I probably see a lot bigger performance gain using this particular type of technique because the increase in size of the using the lookup table, which would be like 10 megabytes for 10 megabytes build, would be a fraction of what would be billed for the amount of data that would be in that column to begin with, spanning over millions and millions and millions of rows. But these are the exact things that you want to be looking at as you're structuring your data and creating your queries. Once you actually have that nice and fine-tuned, using iCharts, you are going to see the same exact level of performance. Create a data set. Oh, let's take a look at this query actually. Create a data set, use the lookup table for the brand product information, use the nested structure for the nested information. Do the cross join and the left join for the nested structure and the lookup table respectively. Don't do any aggregation. The aggregation happens on the iCharts side. That's another important piece, actually, because if you have hard-baked measures into your denormalized data set, as you do different types of aggregations, you may get incorrect values. So we find it more important to use the row-level information, do the aggregations dynamically, do the calculations based off of those aggregations, and not store those calculations in the core data set. Nested lookup. Again, flat data set from the user's perspective. They just think that they have access to all the fields. They don't have to worry about how much data is getting processed. They're just going to see a nice, snappy interface. In this particular case, I'm not even going to bother creating the same exact thing as we did before, because I know that's going to just be cached. So I'm going to actually just, by default, do the brand product to year month hierarchy. And actually, you know what? I will do year month to brand product, and instead of the sum, oops. I will reference the average. Now, I don't believe average will incur any additional bytes processed, but you can see that this is an average on a daily basis across all these brands.
And that's not additive, so that's a good example.
And this is, yeah, that's a great point. This is not additive information. So when we're doing these higher levels of aggregation, we're not averaging all these little values here. We're actually averaging the row level information based off of this this level of hierarchy. Let's go back into BigQuery and look how much bytes we processed. Here's the nice long query where you can actually see doing this average of that particular value as opposed to the sum. And we're doing it for each level of the hierarchy. And again, just 5.71 megabytes processed, 20 megabytes billed. But again, that's going to be tailored to your own data. So when you're actually doing this, don't just think about the size of the data that you're saving or the amount of data that's getting processed. You know, that you may just get a couple megabytes of data in savings. Like here, we only got 20K. But think about like the scale of your data, and then multiply that against the amount of times that people are going to be querying against that data set. And so you'll see that those savings just compound themselves. And you'll be saving more and more as opposed to just saying, oh, I'm going to be lazy and just denormalize the whole thing and forget about it. All right, now we're really going to have some fun. I don't think any customer of ours has a data on a single platform or only from one source. And they often come to us and they say, you know, I can't migrate this data information. You know, BigQuery's a fantastic database, but they're not able to migrate this information. It lives within an application itself, or it may be behind some on-prem system, or maybe within an application that's on a third party and only accessible via APIs or whatnot. And so they're not able to migrate it over, but at the same time, they can't join that information together, so that what they wind up doing is creating two separate reports, and then trying to look at them side by side and see, okay, do these numbers correlate? And even if it were on the same system, and they wanted to do a join between that information, it can be cumbersome to write all that SQL. I mean, I wrote a whole bunch of SQL for these particular demos, but I didn't need to. I basically was able to create a data set and then run the queries myself and do the exploration and the reporting without having to write any SQL. And when you start to add in additional data sources and build those data models, you're not going to want to spend the time creating all these different types of joins and all these different queries to create views or virtual data sets, if you will. You'd want to use a tool like iCharts and our Mashups capability. And what we actually do is when the user is creating a chart on a mashed up data set, which has individual data sets attached to it, iCharts goes out, queries those individual data sets, and creates the aggregate values from those individual sources. And then it will merge the results across the dimensions that are defined within the chart. And so we have a pretty cool example here of how you can do this just purely within SQL, again, but then how you could also do this just directly within iCharts. So this is a data set that we want to bring in. And so we're a CPG company in our mock data set. We've got daily sales, but we also have goals on a month-by-month basis. And those goals are basically our targets for how much we want to sell on a per product basis for every single month. So that's what this particular data set is. You get the year and the month information. We've got our categories: brand owner, brand product data, the region, as well as the department, because we may have different goals for each one of those individual regions and departments, whether or not it's online or in retail. And this particular one here is actually just purely on this Sammy brand. And so in our example, what we'll want to do is we'll want to take this data set here and combine it with the actual sales information to see how well we're performing against the goal. So first I'm going to just I'm just going to show you that table again here. Some little information about the table. This is the structure of it, and the details. It's a pretty small table in and of itself, but as businesses get larger and they want to include budget information, we have some customers that have thousands and thousands of budgets every single month for every single department that they have in every single region. So this kind of data can scale pretty rapidly. It may not reach terabytes and terabytes in size, but that's important to know also. If it's not going to be doing that, you don't want to include that information in your transactional data anyway. You want to keep it separate. So we have a query for it, which basically just gets the year, month, and the brand product and every single amount for the goal. And when we run this query, since it's such a small table, we're only processing 150K of data here. What's interesting to note is we still get billed for 10 megabytes. Now I don't know whether or not this is actually billed per se, where I'm going to see something itemized on a bill here, or it gets converged with some other items in our overall processing. We're doing a lot of processing anyway, but still two metrics to be looking out for within this example. So tiny amount of data is getting processed.
In large data sets, you're going to see pretty much the same numbers as billed and processed, because the blocks are around 10 megabytes.
Oh yeah, okay. So because I love SQL, I actually did this example within SQL to combine the brand product information as well as the brand product and over the years and months to combine the sum of the goals versus the sum of the values to see them side by side. And we're actually using the nested table structure with the lookup table and also doing a join for the product monthly goals here. And for this particular example, our goals are only for the brands that are associated with the word Sammy in them. So I've actually included that as a little set of criteria here. I think it's probably important to note that even though I've included this criteria here, if I didn't include it, it would still just be processing the same amount of data, because it's actually scanning those columns, those individual columns, to find out, okay, which brand product is in that SAMI range. So here we've got 5.86 megabytes processed, a little bit more than the 5.71 or the 5.73 where we're just collecting that information. But since we're using this nested structure as well as the lookup table, that was 5.71 megabytes processed. 5.71 plus the 150 megabytes processed with that other query is actually 5.86. So it's really straightforward. You're just doing the math. You're just adding this information together. And then what we'll actually see here is bytes build is 30 megabytes. Because when I use that nested and lookup table together, that was 20 megabytes build, and with the goals table, it's 10 megabytes. So it's just doing the math. It's just adding those two things together. So this was easy for me to do, but maybe not so easy for some of your other users to think about that. And again, you're not going to want to be creating a whole bunch of virtual tables or views and to create this information. You're going to want your users to define that for you so they can define the data that they want to get. And so from there, we want to actually create a mashup data set. And as I mentioned, the mashup data set will go out and take individual data sources, and I'll be able to dynamically define the mapped fields between those two data sources. And then as I include them into a particular chart, it will go out to those individual data sources, aggregate the data based off the dimensions that I've actually chosen within the chart. So for the first data set, I'm just going to look up my goals information, my goals table. I'm going to add that as a data set. And then for the next one, I'm going to actually enter in a query. Up nested mashup example. And I'm going to get that query that I had for my nested data structure. Not aggregating on anything, wouldn't help us out anyway from a optimization perspective. And add data set. I've got these two data sets loaded. And now I'm going to start mapping fields together. Just going to map year to month, year to month.
Only the dimensions.
Yeah, only the dimensions, and that's exactly right. You really only want to map the dimensions. You don't need to map the measures. Those are going to be too many unique values anyway, and you're not going to put that on a chart, so to speak. Year, month, and brand product. And brand product. Add field mapping. Mashup. Example. So the mashup data set. And now we see a little bit of a different structure in our editor here, where we're actually now seeing that we've got some folders, and these folders actually represent the individual fields from those individual data sets. So I've got my goals data set here, and I've got my brand product sales data set here using the nested lookup table example that we have. And all of these fields here are available for me to use as measures. But these particular fields up here are the only ones that I'm actually able to use as dimensions. You're not going to be able to, and you'll never really want to, create a mashup only to use a field that is only in one single data set. It doesn't make sense. You're not going to be able to get any information from the second data set, and you're basically just wasting your time. But so what I'm first going to do is I'm going to add a filter here for the brand product, because I said I only wanted Sammy's data here. So I'm just going to select these particular values. One more. Apply. And then I'm going to bring my brand product information here. Oh, and actually want to look at that same example, your month. And now that, since I'm only looking at the Sammy's information, much fewer rows within that row level data. And now I'm just going to pull in the values, my goals value. Here's my goal. Now it just goes to that one data set to get the goals information, puts it in my pivot table. And then I can also see my values side by side. All right, great. I'm able to see data from two different data sources. They could be from two explicitly different systems. These particular data sources, yeah, sure, they were both on BigQuery, but I could have gotten the goals information from NetSuite. I could have gotten it from a JDBC data source. I could have gotten it from anywhere else.
SQL, MySQL,
SQL, yeah, SQL, MySQL, Spanner, other awesome Google products. Bigtable, Bigtable over BigQuery. We did a great demo of that back in March. And now we'll go back, refresh my results queue, and see if it actually cached that. And for this, I'm actually, query history. For this, I'm actually going to be looking at two separate queries. One for the nested lookup example, and one for those product monthly goals. So for the product monthly goals, awesome. It didn't cache the results. I'm getting 150K bytes processed, 10 megabytes bytes build. And in my nested structure, I'm getting 5.71 megabytes processed, and again, that 20 megabytes build. This is for the nested lookup table that we have. And so add those two together, it's the same amount, 5.86 megabytes processed, 30 megabytes build. But the overall end visualization of these two fields is occurring on our end. So if I actually made a calculation between these two fields or added some more additional stuff to it, that stuff would happen on an aggregate level within iCharts. So you're not going to be incurring any additional processing within BigQuery just to combine the information together.
I have one small note regarding, can you bring the nested query with the left joins? And
Oh, yeah.
just want to make a point, which is very important. If one of your engineers is going to show you this query, you're going to probably fire them. Doing cross join, it's something that you don't want to see in your code, and left joins, it looks like super inefficient, especially on nested structured data. You might think that you're going to be processing exponential amounts of data by doing that. And that's also preventing some of our customers to try nested structures because they say, hey, you know what? It's very efficient to store my data in this way, but the query is going to kill us and it totally doesn't make sense. So this example shows you that if you know what you're doing, and in iChart we know how to take advantage of exactly those strengths in BigQuery, you can run lean and mean by doing very nasty SQL queries, which George showed us today. And that's a very important point. And again, you don't have to use our tool and run back to BigQuery and compare the queries. You can rest assured and understand that we're going to take any measure to make sure that the query is going to be as optimized as possible going to BigQuery, even though that sometimes it looks very scary.
Mm-hmm. Yeah. That's a great point, and I think that's really a paradigm shift that people have to make between using a traditional database, which will scan the entire table or scan columns over and over again, versus BigQuery, where it scans the columns that you're using just once. And so when you're doing things like with the nested data structures or using some joins, it takes that data it takes the fields that you've chosen within your query, scans it once, and then does the processing across that single scan. So yeah, you can blow it out, but I don't think that you'll actually see the amount of data processed blow up as well. All right, I think that pretty much wraps up our demonstrations here and our presentation for part one of optimizing your data within BigQuery. Just some final notes. Again, your mileage may vary. It all really depends on your data and how well you're able to take advantage of things like lookup tables and nested structures. So you really got to know your data and just take time to structure it efficiently. Again, think about the scale of your data. If you're only getting a 5% increase in optimization, think about that for how many times your data sets are going to be queried using the techniques that you've implemented versus not. And so if you'd like to get invited to our next webinar, we're going to be having a few of these on some additional ways to use BigQuery as well as iCharts, or you'd like to take a test drive of our product. Or if you have questions about your data, how we can help you answer those questions and gain insights into your data, help you get those insights into your data, just send a note to Rico here. He'd be happy to put you in touch with the right people. Thank you very much. Really appreciate it.
All right. I think that wraps it up. Thank you all for joining us, and we look forward to the next time.